Hello viewers of AraaTech. Today we are presenting new topic adversarial attack and artificial intelligence. Let's start. Definition. Adversarial attacks in transfer learning and artificial intelligence refers to the intentional manipulation of input data to deceive or mislead machine learning models. These attacks exploit vulnerabilities in the model's decision-making process, leading to incorrect predictions or classifications. Adversarial attacks can compromise the performance and reliability of artificial intelligence systems, posing significant challenges in various domains, including computer vision, natural language processing, and reinforcement learning. Examples. To illustrate adversarial attacks in transfer learning and artificial intelligence, let's consider a stepwise example in the context of image classification. Understanding the target model. Suppose we have a pre-trained convolutional neural network CNN model for image classification. This model has been trained on a large data set of natural images and achieves high accuracy on various classification tasks. Crafting adversarial examples. The attacker aims to craft adversarial examples that appear similar to the original images but led to incorrect predictions by the model. Using knowledge to the model's architecture and gradients, the attacker computes perturbations to add to the input images. Adversarial perturbations are typically constrained to be small to remain imperceptible to humans but effective in fooling the model. Generating adversarial images. By adding carefully crafted perturbations to the original images, the attacker generates adversarial examples. These adversarial images look visually similar to the originals but can cause the model to misclassify them. Transfer to a target task. Suppose the pre-trained CNN model is fine-tuned on a smaller dataset for a specific classification task, such as recognizing different types of animals. The attacker transfers the adversarial examples crafted for the original task to the target task without the need to recraft them. The transferred adversarial examples maintain their effectiveness in fooling the model, even though it has been fine-tuned on a different dataset. Impact on model performance. When the model encounters adversarial examples during inference, it may misclassify them with high confidence, leading to potential security risks or safety hazards. Adversarial attacks highlight the vulnerability of machine learning models to carefully crafted perturbations and underscore the importance of robustness and security measures. Conclusion. Adversarial attacks in transfer learning and artificial intelligence pose significant challenges to the security and reliability of machine learning models. Understanding the mechanisms behind these attacks and developing robust defense strategies are essential for building trustworthy artificial intelligence systems that can withstand adversarial manipulation. Here is a more detailed explanation. Transfer learning is a powerful technique in machine learning and neural networks that leverages knowledge learned from one task or domain to improve learning and performance on another related task or domain. Here is a breakdown of the key points you mentioned. Knowledge transfer. Transfer learning involves transferring knowledge gained from solving one task, source task, to improve learning and performance on a different but related task, target task. This is based on the intuition that knowledge learned in one domain can be useful for learning in another domain. Pre-trained models. In the context of neural networks, pre-trained models are networks that have been trained on a large dataset for a specific task, such as image classification or natural language processing. These models have learned meaningful representations of the data that can be beneficial for other tasks. Fine-tuning. Fine-tuning is the process of taking a pre-trained model and further training it on a smaller dataset for a specific task. During fine-tuning, the weights of the pre-trained model are adjusted to better fit the new data and task. This allows the model to adapt its learned representations to the characteristics of the target dataset while retaining the general knowledge gained from the source task. Benefits of transfer learning. Faster training. By starting with a pre-trained model, transfer learning reduces the amount of training time required for the target task. Better performance. Transfer learning often leads to improved performance on the target task, especially when the target dataset is limited or the task is similar to the source task. Generalization. Pre-trained models have learned generic features from a large dataset which can help improve the generalization ability of the model on new tasks. Applications. Transfer learning is widely used across various domains including computer vision, natural language processing, speech recognition, and reinforcement learning. It has been successfully applied in tasks such as image classification, object detection, sentiment analysis, and machine translation. Overall, transfer learning is a valuable technique that enables the reuse of knowledge across tasks and domains, leading to more efficient and effective machine learning systems. Intentional perturbations. Adversarial attacks involve the deliberate manipulation of input data to deceive machine learning models. The attacker aims to introduce small, carefully crafted perturbations into the input data, such as images, text, or audio, with the goal of causing the model to make incorrect predictions or classifications. Deceiving the model. By perturbing the input data, the attacker seeks to exploit vulnerabilities in the model's decision boundaries or feature representations. These perturbations are often imperceptible to human but can lead to significant changes in the model's output, causing it to misclassify the input data. Imperceptible perturbations. Adversarial perturbations are crafted to be subtle and indistinguishable from the original input data by human observers. Despite their small magnitude, these perturbations can have a disproportionate impact on the model's behavior, highlighting the sensitivity of machine learning models to adversarial manipulation. Targeted models. Adversarial attacks can be targeted towards various types of machine learning models, including those used in transfer learning, whether the model is a simple linear classifier or a complex deep neural network. It can be vulnerable to adversarial attacks if it relies heavily on the specific features or patterns present in the input data. Examples of adversarial attacks. Evasion attack. In evasion attacks, the attacker perturbs input data to cause the model to misclassify it. For example, in image classification, an adversarial image might appear visually similar to a stop sign but be misclassified as a yield sign by the model. Poisoning attacks. In poisoning attacks, the attacker manipulates the training data to compromise the model's performance during training. For instance, in spam email detection, an attacker might inject carefully crafted spam emails into the training dataset to reduce the model's accuracy on detecting spam. Black box attacks. In black box attacks, where the attacker has limited knowledge of the model, adversarial examples are generated using only input-output queries to the model without access to its internal parameters or architecture. Impact and implications. Adversarial attacks pose significant challenges to the security and reliability of machine learning systems particularly in critical applications such as autonomous vehicles, medical diagnosis, and cybersecurity. They highlight the need for robustness and security measures in machine learning models, including adversarial training, input sanitization, and model assembling. In summary, adversarial attacks represent a serious threat to the integrity and trustworthiness of machine learning models, including those used in transfer learning, and underscore the importance of developing robust defense mechanisms to mitigate their effects. Types of adversarial attacks. White box attacks. Description. In white box attacks, the attacker has complete knowledge of the target model, including its architecture, parameters, and training data. This allows for more sophisticated and targeted attacks. Example, the attacker can compute precise adversarial perturbations using gradient-based optimization techniques, exploiting vulnerabilities in the model's decision boundaries. Black box attacks. Description. In black box attacks, the attacker has limited knowledge of the target model and can only interact with it through input-output queries. This makes crafting adversarial examples more challenging but still feasible. Example, the attacker may generate adversarial examples by querying the model with carefully chosen inputs and observing its responses without access to internal model details. Transfer attacks. Description. Transfer attacks involve crafting adversarial examples for one model and demonstrating their effectiveness against another model, even if the models are trained on different datasets or have different architectures. Example, adversarial examples crafted for a convolutional neural network CNN trained on ImageNet can successfully fool a different CNN model trained on a distinct dataset, showcasing the transferability of adversarial perturbations. Evasion attacks. Description. Evasion attacks aim to perturb input data in such a way that the model misclassifies it. The attacker seeks to manipulate the input to cause the model to make incorrect predictions. Example, an attacker modifies an image of a panda slightly so that a deep learning model misclassifies it as a gibbon with high confidence, even though the perturbation is imperceptible to humans. Poisoning attacks. Description. Poisoning attacks involve manipulating the training data to compromise the model's performance during training. The attacker injects malicious data points to manipulate the model's learned decision boundaries. Example, in a spam email detection system, an attacker adds carefully crafted spam emails to the training dataset to decrease the model's accuracy on detecting spam messages. Defenses against adversarial attacks. Adversarial training. Description. Adversarial training involves augmenting the training process with adversarially perturbed examples to improve the model's robustness. Example, during training, both clean and adversarially perturbed examples are used, encouraging the model to learn more resilient decision boundaries. Defensive distillation. Description. Defensive distillation involves training the model with softened probabilities to make it less susceptible to adversarial attacks. Example, instead of training the model to predict the most likely class, the model is trained to output softened probabilities across all classes, making it harder for the attacker to exploit. Input pre-processing. Description. Input pre-processing techniques apply transformations to input data to remove or reduce adversarial perturbations before feeding them into the model. Example, adding noise to the input data or applying image transformations such as random rotations or Translations can help mitigate the impact of adversarial perturbations. Adversarial example detection. Description. Adversarial example detection involves developing algorithms to detect and filter out adversarial examples during inference. Example: utilizing anomaly detection techniques or measuring the model's uncertainty can help identify inputs that deviates significantly from the model's expected behavior, potentially indicating adversarial examples. Conclusion: adversarial attacks pose significant challenges to the security and reliability of machine learning models. Implementing robust defenses and continuously researching new mitigation techniques are crucial for building trustworthy artificial intelligence systems resilient to adversarial manipulation.